So I have started the recording. Now I'll start sharing my screen. So I hope my screen is visible to all of you. Again, like someone can tell me. There are 8 people as of now, including me.
Visible, sir.
Okay. So this is basically the PMRF TA session for NPTEL CS52 Reinforcement Learning course. And this is taken by Professor Balaraman Ravindran of Computer Science Department in IIT Madras. And I am a Prime Minister Research Scholar from IIT Bombay in Computer Science Department. And basically, we get this fellowship from Government of India, and in return, like we have to teach like for 25 hours per semester. So this course like is divided over 12 weeks. So for each week, like we will be conducting like 2 hour session each, and in the end, like just before your exam, there will be one extra help session. So it makes it 25 hours. So like this is the week one session. So details of the weekly live sessions are like when to attend is like this session is conducted on Tuesdays, like from 6 to 8 p.m. And like actually there are three sessions going parallelly. So one is on Saturday, one is on Monday, and one is on Tuesday. So these are like taken by different TAs. So like it's just to ensure that whenever you are free, you can attend that session. It's not mandatory that you have to attend all three. You can attend, but like it's generally recommended to like start attending one session and stick with it. And where to attend is Microsoft Teams on the same link. And then who can attend is like anyone who has taken this course. And why to attend? Like basically like I'll be discussing like your practice assignments and assignments also, but I won't be giving you answers for the assignments, but I'll guide you through to the answers, and you guys will give me the answers for these assignments because your assignment deadline is still 7th of February. So like second reason to attend this is like I'll be solving some problems apart from this practice assignment and assignment, which will help you in your exams later. And obviously like there will be doubt clarification also. And third biggest reason to attend this session is like there will be two-way communication. So I will be communicating with you. You will be interacting with me. So generally, like in lectures, you are given recorded lectures. So you don't have the opportunity to interact with someone of associated with this course. So this like these kind of sessions ensure that that interaction happens. Now, what are the expectations? So there are few expectations from my side to people who are attending these sessions. First expectation is that you should have watched the weekly lecture video. So this is for like week one. So you should have watched the week one content. Like there are 5 lecture videos. You should have watched them before attending this session. And you should have at least tried to attend the weekly assignments and practice assignments. I'm not saying that you should have got to the correct answer, but you should have at least made an honest attempt at them. And generally, like it is recommended to read the Sutton Barto book. So this is like very this book is known as the Bible of reinforcement learning. So if you have time, you can read it. But watching the lecture videos with that, if you are able to read this book, then it will be really helpful in understanding the topic. And the slides of this session will be made available. Also the recordings of the session. But don't like try to wait for the recordings because these recordings and slides might be shared to you quite later. Like I will be sharing them to NPTEL like today only, but they might be shared with you at a later date, and it might be like after the deadline passes. So like it is recommended to attend these sessions. Now the guidelines for these sessions. So like generally like it is recommended that you guys keep yourself muted so that there is no background noise because this is recorded. People who cannot attend these sessions due to some reason, they will be watching them later. So it is necessary to avoid the background noise. And if you have any doubt you can ask in chat also. But the recommended thing is to unmute yourself at that point and ask that at that point itself. And one more guideline is that try to be responsive and try to solve the problem simultaneously, because this session is mainly for problem solving. So if you can have pen and paper with you, you can follow along. And whenever required, like I'll be giving you guys time to solve the problem, like a couple of minutes, maybe if some calculation is required. And this is the order of the session. So first, like I'll be discussing the practice assignment, then I'll be discussing 10 more problems, and then I'll provide a demo. So this will be a code-based demo of like bandits, which we saw. Like this will basically demonstrate the exploration exploitation dilemma through a game. And at last, I'll be providing some guides like on assign how to solve these assignments problem. I won't be giving you answers, but I expect that if you are able to get the concepts right, then you will be able to get the answers also. So audience interaction. So like this is the first session. So I need to know like what is the audience coming from? Like audience, is it like maybe like I'll ask you guys from the chat itself. So like there are almost 10 attendees. So maybe you can introduce yourself like you are bachelor's student, master's or PhD student, or you are professional, like maybe from industry or academia, so that I can get to know like my audience is. So maybe like I'll go in order. Like first, Dhairya Sachdeva, you can introduce yourself. You can unmute.
Hello, am I audible?
Yeah, yeah,
Hi everyone, I'm a BTech CSC student from JP Institute, Noida.
right.
Currently, I'm pursuing BTech, and with it, I'm also doing an internship.
Mhm.
So that's all about me.
So why do you want to take this reinforcement learning course?
Actually, I've been doing quite a lot of AI through my college time.
Right,
So reinforcement learning is one of the fields where I want to learn more. That's why.
right. Okay. Now next is Karthik.
Yes, sir. I'm Karthik and I'm from Tamil Nadu. I'm
Right.
currently studying. Sir, I'm from Tamil Nadu.
Yeah, yeah. So you're doing your bachelor's or master's?
BTech, BTech in
BTech.
AI.
Okay, okay, right. So again, like the same question for you also, why do you want to take this reinforcement learning course? So this is a common question. Others can also answer this when I come to them
I want
later.
to I want to
Yeah.
improve it as a skill, as my
Mhm.
faculty told to take this RL for the
Right.
better AI concepts.
Yeah.
That's why I do.
Yeah. So like your faculty is correct. Like this reinforcement learning is a very important topic, and in future, like it will become even more important because this is the way in which humans learn. This is the most natural way to learn. Yeah, so someone in chat asked like why RL to explore newer dimension of machine learning. Yeah, this is one of the reasons. So Mohini has already given her introduction. So she is a faculty and also continuing her PhD. So due to audio problem, she has written in chat. So yeah, like this is one of the dimension of machine learning apart from supervised learning and unsupervised learning. So mostly like in most colleges, supervised learning is taught well. So even unsupervised learning, but reinforcement learning is not taught at that much level currently. So like this is a like really good course for you guys to take. Now next is okay, so there is one new person, Jagrati. Maybe you can introduce yourself and tell me like your bachelor's students or masters, and also like why you wanted to take this course. Okay, Jagrati, I think we are not able to listen. Maybe I'll move to Keshav. So Keshav, can you introduce yourself? Okay, think again. So maybe next is M. Lakshmi Narayan. So now like maybe we'll move to Moniha PS.
Good evening, sir. I am pursuing my second year BTech AADS in Sri Ramakrishna Engineering College, which is located in Coimbatore, Tamil Nadu.
Right,
In this semester, I'm having machine learning as a subject. So I wanted to take this reinforcement learning course.
right. Got it. So yeah, who was speaking? Yeah, so maybe next we will move to Shankar Lal.
Good evening, all, sir.
Yeah,
I'm working as an faculty in mechanical engineering department in Chennai. I
right.
want to get the domain certificate in data science. That's why I have selected this course.
Okay, got it. Next is Aisha. So maybe we'll move to Supriya. Supriya, if you can unmute and introduce yourself. Uh, okay, we'll move to Suresh.
Good evening, sir. This is Suresh from Andhra
Right.
Pradesh.
Yeah.
Actually, I'm studying BTech today. I'm BTech
Mhm.
in my.
Okay. So last is Thami Zarasi and
Good evening, sir. I'm
yeah,
Tamil.
right,
Actually, I'm doing a PhD in NIT Tiruchi. So,
right.
as a part of research, I just want to learn reinforcement learning, which will be helpful for my research work.
Okay. So got it. So our audience is quite diverse. Like there are bachelor's students also, PhD students also some faculty. So like this helps me like in order to do the expectation setting. So is there like are there some expectation from your side? If there are, maybe you can mention so that I can take a note of them and like try to solve them in like the next sessions. If there is some expectation of you from me. Okay, so it seems there is no more. So okay, I'll move to, so you guys can see the slides, right? Maybe someone can unmute and tell me, like these are the like week one topics which were covered in the lectures. So introduction to RL framework and applications, introduction to immediate RL, in which like rewards were given immediately, then bandit optimalities and some value function based methods. So I hope like you have watched the lectures of these. And now like we will start with our first section, which is like practice assignment one. So the first question is, which of the following best suits the notion of regret in a standard multi-arm bandit problem? And the bandits are assumed to be stationary. So the first option is like the difference between the total reward that could have been achieved by choosing the optimal action. So from the beginning and the total reward achieved by choosing the worst action. Is this like one of the option? Is this like the definition of regret? So basically in this question, like they have asked us the definition of regret. Is this the definition of regret first option? Like the difference between the total reward which we could have obtained if we choose optimal action from the beginning and the total reward achieved by choosing the worst action. Generally, like we don't focus on the worst action. Like, so this is not the right answer. So the second option is the number of time steps required for the solution method to find the optimal action. So this is like something different, right? This is what is called as spec optimality. This is not the notion of regret. Now, the third option is the difference between the total reward that could have been achieved by choosing the optimal action from the beginning and the total reward accumulated by our solution methods. So this is generally the graph, right? In which, like, suppose this is the optimal action reward, and we generally move like this way. So this region becomes the regret. So this is the right option. Second one is not the right option. And the last one is the difference between the best possible reward that can be sampled by selecting the optimal action and the worst possible reward. Again, like this is not the definition of regret. So this is not the right answer. So the correct answer for this one is C. So is there any doubt regarding this? If not, like I'll move to the second question. Okay, then I'll move to the second question. So second question talks about assignment problem. So what is this credit assignment problem? So it is the issue of assigning a correct mapping of rewards accumulated to the actions that led to them. So think of the game of chess. So we might have made some move in the beginning, which might have resulted in the win in the end of the game. But how to, like, in between, like we weren't getting rewards. The reward is given at the end when we win the game. So how to map this reward to the action which actually resulted in that? So this is the problem of credit assignment problem. So this problem is like quite complex in reinforcement learning because we want to assign the appropriate credit to the action that caused the reward. But like the major reason why this is hard is because rewards come at a quite later stage. So which of the following is the reason for credit assignment problem in RL? Rewards are restricted to be a scalar value. Can this be the reason? Like, I don't think so, because like even if rewards are not restricted to scalar value, like if they are vector, then we will have to assign the each component of vector to the correct action. So the problem still remains. So rewards are delayed in RL setting. This this is the reason actually, because rewards come at the later stage. If the rewards were immediate, then we could have simply said that this is the last action caused this reward. But since the rewards might be delayed, then due to this credit assignment problem is a issue. And the third option is agent cannot observe the reward. This is again wrong because agents, like RL works through reward framework. Agent has to observe the reward after each action. And the fourth option is RL agents do not face the credit assignment problem. This is again all wrong because they face this credit assignment problem. So is there like any doubt in this? Like, so the correct answer here is D. So if there is no issue, then I'll move to the third problem. So this is actually like asking for solving. So consider a standard multi-arm bandit problem. So the probability of picking an action using the softmax. So this is the like formula of getting the probability if we are using the softmax criteria. So they have given us values, Q values for each action. So there are like 4 actions, A0, A1, A2, and A3. And the question they are asking is that we have to calculate the probability of picking an action. So is given by now the current value estimate. So this one, so I think there is some missing part. So basically, like in this question, what is asked is you have to find the probability of action 2. So basically A2. So what is the probability of this A2? So basically, like you have to simply put the values here. And when you put the values here, so it will be like, so in numerator, we will have E raised to. So what is the Q value of this action? So the Q value of this action is action 2, we are considering 0.5. And the temperature, again, like this question is incomplete in the like assignment. So the temperature parameter is also given to be 0.5. So this beta, you can take it to be 0.5. So again 0.5 upon 0.5. So this will be the denominator. Now we move to our, this will be the numerator. So we move to our denominator. So denominator will be E, and zeroth action is 1, again upon 0.5 plus E. Now again it's 0.2 upon 0.5 plus, this is the same as our numerator. So E, this is simply, this will cut out. So it will be 1 only, plus E raised to power minus 1 upon 0.5. So basically, like in this problem, you don't have to do much. It's just a calculation question. So it will become E upon E square plus E raised to power 0.4 plus E plus E raised to power minus 2. So basically, like you have to put these values and get the solution. So maybe like I'll give you 2 minutes to like solve this. So you guys know the value of E, right? The value of E is 2.718. You can take it to be 2.72. So maybe like 2 minutes you can take and try to solve this and see like which of the four options is the answer. So I understand that this question is lacking some of the important information, like they didn't provide the value of beta, which is 0.5. And again, they didn't even mention like what is asked. So the thing that is asked is probability of action 2. So maybe you can take 2 minutes and try to calculate this. Let's see like who does it first. When you are done, like I'll give you 2 minutes till 6:30, and let's see who can do it in till 6:30. Meanwhile, I'll also do it. 2.6 square is plus, this will be 1.49 plus 2.72, and this will be 0.13. So it turns out to be 2.72 upon 11.72. And when you solve it, what will you get? Can anyone answer this? This is quite simple, right? Like maybe an approximation. There are 17 people, including me. So can anyone like answer? Like, so people, I think they are writing in chat. So, okay. So it's 0.3, right? Okay.
0.23, sir.
Yeah, 0.23. So which is the like correct option? So it's option C.
C.
So yeah, so this is the like correct option. Now we move to like question 4. Like in this slide, basically we have to tell like which of these statements are correct. So the first statement is the rewards are obtained at a fixed time. So the keyword here is fixed time after taking an action. Suppose we are playing the game of chess. Like, do we know that after an exact 10 moves we will win? We don't know. Like the game might take 20 moves or it might get finished in 2 moves. like after taking an action. So we don't know like whether this time will be fixed. So are the rewards obtained at a fixed time? No, this is variable. So second thing is reinforcement learning is neither supervised learning nor unsupervised learning. Like, yeah, we know that ML is divided into like three big classes. One is like supervised learning, second is unsupervised learning, and third is reinforcement learning. So in supervised learning, we are given the labels, and in unsupervised learning, we aren't given the labels. So this is more like pattern matching or clustering problems. And in supervised learning, we encounter problems like classification and regression. In reinforcement learning, we learn by interacting with the environment. So this is something which has that online feature, online learning kind of feature in which we interact with the reward. We don't have the data like in the hand beforehand. So we need to interact with the environment and then the environment will come off with a reward. So this way, like reinforcement learning is different from these two. So apart from these, like there are some more kind of learning. Maybe you guys might have heard of. So there is one called semi-supervised learning. So it is like semi-supervised learning is something between the supervised learning and unsupervised learning. So supervised learning, you are given labels for each of the data point, and in unsupervised, you aren't given labels for any of the data point. So in supervised, semi-supervised, what happens is you are given labels for some of the data points, but other data points you aren't given labels. So some fall under like some have labels and some are label less. So this problem is like quite prevalent in medical domain. So in medical domain, like you'll have a lot of data points, but the person who will be assigning labels, he might not be able to do it. Suppose there are 1 lakh data points and there is a doctor who needs to assign labels whether this is actually disease or this person doesn't have a disease. So there are two levels, whether this person has a disease or this person doesn't have a disease. So he can do it maybe for 100 data points, but like for 1 lakh, like it's hard. So in those cases, this semi-supervised learning comes. So this is also one form of learning, but generally like ML is divided into supervised learning, unsupervised learning, and reinforcement learning. And reinforcement learning is neither supervised learning nor unsupervised learning. So this is correct. So two reinforcement learning agents can learn by playing against each other. Is this possible? Like I remember like in lecture, sir discussed this is called something. Can anyone like tell me the name of
Self
that
play.
term? Self-play. Yeah. So self-play also like I think sir also mentioned there was a game in which this self-play was used. Can anyone tell me the name?
Backgammon.
Backgammon, right? So this is like so this option is also correct. Two reinforcement learning can learn by playing against each other. And not just like in backgammon, like that agent was TD Gammon, even in like newer games, like these chess agents and even for Ghosts. So there is this component of self-play. So it is still there. So this self-play is there. So two RL agents can learn by playing against each other. So generally what happens is suppose we have two instances of an agent. First, we will like kind of freeze one of them and train this on this. Then we will freeze this and then train this on this. So in this way, like they can improve from each other. So generally, like we learn better if we have a strong opponent. So maybe for example, India is like not that good at football. So if we play like good opponents, then our learning will be more rather than playing with like weaker opponents. So it's the same analogy here. So two reinforcement learning definitely can learn by playing against each other. So the fourth option is always selecting the action with maximum reward will automatically maximize the winning probability in a game. Is this correct? And maybe someone can unmute and answer me or write in chat. Like the key term here is always. So maybe I'll give you an example. Suppose in chess, we are in a state where like we have the option of capturing the queen of the opponent, and this will give us maybe +3. But this might lead to a position in which we get checkmate and we lose the game to -10. So at that point, like this +3 was the highest reward we could have achieved, but maybe later we lost the game. So this will not automatically maximize the winning probability. But maybe if we moved from this state in which we didn't capture the queen, maybe like we got a reward of 0, but eventually it leads to some stage in which we captured the king of opponent. So this gives us a +10 reward, maybe +100 for a win. So like it will not always maximize the winning probability. So the key term here was always. So this is also again not correct. So the correct options are 2 and 3, right? So option C. So are there any doubts till now? Like this segment is over. So if there are any doubt in any of the 4 questions, maybe you can ask me now. So I think like there are no doubts. So, so probably the reason is because these questions are relatively simple and you could have reached the answers also because you can submit multiple times and try out different combinations in practice assignment. So now we will move to the second section, which is the problem solving. So in this section, like I will be solving problems which haven't been given to you. Like these problems aren't part of neither the practice assignment nor the assignment. So like let's begin with question 1. So in this section, maybe you guys can try out. So which among the following are features of a reinforcement learning solution to a learning problem? So a learning problem, like it can have many solutions: supervised, unsupervised, reinforcement learning. So this question is concerning the reinforcement learning solution. So what are the like features of reinforcement learning solution? Is it like a trial and approach error to learning? Like we learn by trial and error. We try different actions, get a reward, or we make an error and get punishment. Can anyone answer? We'll see in chat if something is there. Yeah, so yes. So yeah, like this first option is correct because it is a trial and error approach to learning. So is like exploration versus exploitation dilemma part of reinforcement learning solution? So this like even sir has discussed a lot in the lectures. Like the focus is to balance this exploration and exploitation. So like we need to know like at what point we need to stop exploring and start exploiting so as to maximize the reward, long-term reward. So this is also one of the features of reinforcement learning solution. Is it learning based on rewards? Definitely. Like rewards is something which acts as the feedback in the reinforcement learning problem. So this is one of the features. Now the fourth option is the most important one. So like in the previous section, the questions were like in which like only one of the option was correct. Here like multiple options can be correct. So A is correct, B is correct, C is correct. But my question is regarding question D. In reinforcement learning, is this one of the features of reinforcement learning? Absence of any feedback or supervision? I think someone answered yes. One no also. So the question is like, is this feature of a reinforcement learning solution? Like the key term here is any. Like basically like if there is no feedback, then how will you learn? So there must be a feedback. So in reinforcement learning, feedback is given in terms of reward. It might be delayed, or might be immediate, but there is a feedback in form of reward. So it is actually present. So this option is wrong. So the correct options are A, B, and C. Feedback is there. Like maybe this term supervision might have caused some issues, but like the feedback is there in terms of reward. Although it might be delayed, it might come at a later stage. So like, is there any doubt in this one? I think like this is quite simple. So maybe like I'll move to next question. So I think like if someone has attended the lecture, he should be able to answer this. Modeling a living organism as an RL agent. So the environment encompasses. So generally the definition of environment is everything that is outside the agent is called the environment. So what is the answer of this? Everything external to the organism or some portions internal to the organism as well are part of the environment. So for this one, like I'm expecting the answer from you. Is it like option A or option B? So we have like option A also in chat, option B also. Okay, so there is no common consensus. So maybe like I'll give you the answer. So the actual answer for this is option B, because like the rewards in, suppose we consider human beings only, like rewards are realized inside the brain. So like the senses like your arms, eyes, ears, they are also part of the environment because they are just delivering that signal to the brain. Once it comes to the brain, then brain converts those like sensory information, which is the observations, like these will comprise the state variables, and that will be mapped to reward. So this is happening inside the brain. So some portions internal to organism, which might be eyes, ears, or our sensory organs. So these can be part of the environment also. So the answer is B. Is there any doubt in this? Okay. So we'll move to question 3. So it was mentioned in lecture that reinforcement learning solutions have to be able to handle delayed rewards. So what exactly are the problems that arises due to delayed rewards? Is there a problem in storing rewards? Like this cannot be a problem, right? Because like nowadays we have a lot of computation, like storage power, like it's become quite cheap. And even like we have cloud facilities where we can like purchase some kind of subscription to Google Cloud and store there our data. Even Google Drive provides an extra subscription. So like this is not really a problem in storing the rewards. Problem in assigning rewards to the action that caused them. This is a problem because like this we have discussed before also. This problem is called something. So even the option C, problem in mapping states to the rewards that can be achieved from those states. So first we will discuss option B. Like this problem is called something. In one of the previous question, we saw this problem. Can anyone answer like what is the name of this problem? So problem in assigning this, keep this word assigning in mind. Rewards to the action that
Credit
caused them.
assignment.
Yeah, so it was the problem of credit assignment. So this is the problem actually in reinforcement learning. So option B is the problem. Again, like, so in credit assignment, we are assigning the reward to the action, but we need to map the reward to the states also, because like this reward, maybe this will be told to you later. This is a function of state also and reward also. Suppose like if we are sick, if someone is sick and there's a lot of exercise, then he will get like tired very easily or might even become even sicker. So he will get a negative reward. But if someone is healthy and he does exercise, then like he will get a positive reward. So this way, like it depends on state also. So this problem is also there. Problem in mapping states to rewards. So the option here is B and C is the incorrect one. So is there any doubt regarding this? I think there shouldn't be. Okay, then I'll move to question 4. So question 4 mentions that in the tic-tac-toe problem, it can be observed that many board positions are symmetric. So assume an imperfect opponent. Imperfect means like he is not perfect. So tic-tac-toe is not really a very difficult game. In tic-tac-toe, like there exists an strategy. If there is a perfect opponent, he will not let you win. So there is a strategy in which like it will result only in draws or might even result in a loss for us. And the opponent, if he is like perfect, if we make a mistake, then he will capitalize on it. So here we are assuming like it's an imperfect opponent and he is following a stationary policy. So what is stationary policy means like it doesn't change with time. So like he has a policy beforehand and it's not like seeing our moves, he is adapting his policy. His policy is fixed. And that opponent is taking advantage of the symmetries in the board positions. Okay. So which of the following are true? If we also, so opponent also is also using symmetry and we are also taking advantage of symmetry. So like which of the following options are true? If both of us are like taking advantage of symmetry. So if like there are states like suppose I'll draw some. So this is one state. Maybe. So it could have been reached in different ways, right? Maybe we played X first and then the opponent played 0. But in tic-tac-toe, like like next move should only depend on that state, not how it was reached. Because this is basically called as the Markov property. So like here, like these two states, regardless of whether we put X first here or X first here, like these two states will be equivalent. So, but like this will help in like reducing the time taken to learn the values because like instead if we were considering history then we will be learning like if we were not taking advantage of the symmetry then we will be considering this state and another like same state but reached in a different way. Maybe like this one was written first then second one and this one was written second and this one was written first. So these two will be like different states if we don't take advantage of symmetry because tree grows like the search tree of games, like first move, then second move. So like similar states might arise like at different nodes. So, but if we like take advantage of symmetry, then we can like reduce the time to learn those values because there might be like many states, like it could have been reached in many ways. So we can reduce the time to learn the values because we will be doing it only once for many of these options. And also like space required to store the values will reduce because earlier we might be storing it multiple times. Now we will store it only once. So that so these two like are correct. So the final policy learned in this approach is better than the policy learned when not taking advantage of symmetry. This is an important question. So can anyone like try to answer like, is this also true? Like final policy learned in this approach is better than the policy learned when not taking advantage of symmetries. Maybe I'll see in chat. So there's a question, how come space reduces? So space reduces because like we like if we were maintaining some kind of table for each, so this will maybe S1, this is S2 state. So we will be storing for S1 separately, S2, even though the value will be same. but we will be storing it twice. So now like we can store it only once. So we can we can use some data structure like pointer or something to like map to one value only. We can store at one place and we can assign pointers to this value to all the states like which are similar. So in this way, like space also reduces. Yeah, like all the states need to be maintained, but like you can like kind of use like you need to store the variable once only. So instead of storing the variable multiple times, you can store at one place only. Like suppose this table is there of q values, suppose. So instead of storing at this exact block, you can simply assign a pointer. Pointer takes less space and you can store at some other place one variable and both of them can point to this. So maybe like if pointer was taking point one of the space, so if we were storing both, so we will be using up two space. But if we are storing only at one place, like it will be 1 plus 0.2. So in this way, like we are reducing the space. Okay, so option C. Someone said option C is it like true or false? There is a true. There are true actually, three true. So maybe like I'll explain like it will not be better policy because like it's just that for each of the state we are doing it many times. So we are like using extra time, we are using extra space also, but like will this be better in some way? Like redundancy, reduction of redundancy will not lead to a more intelligent policy, right? So this is actually wrong. Like this is not true. It will not result in a better policy, but we will be able to reduce the time and space. That is the point here. So I hope like everyone got it. No, exploration will not be missing because like these two states are actually equivalent, right? We don't have to explore them multiple times. No, no. So these two states are same, like in the sense that they are symmetric. I mentioned the Markov property. So once we reach that this state, like we don't need to explore it like twice. So even if we like store it once, we can explore it twice from that place also. So this will not result in a like better policy, but it will reduce the time and space. I hope you got it. Yeah. So like this is the question 4. Now we will move to question 5, which is a continuation of this question only. So considering again the question of taking advantage of symmetric board positions, is it necessary that symmetrically equivalent positions should necessarily have the same value? So one key point to note here is like in this like only we are taking advantage of this symmetric board positions. The opponent, like in previous question, opponent was also taking advantage of symmetry. In this question, it is not mentioned that opponent is taking advantage or not taking advantage. So that assumption is not valid here. So keep this in mind. So now considering this, like, is it true that the symmetrically equivalent positions should necessarily have the same value? Like this is a question regarding a corner case in which you have to think about a corner case. So is it like no or yes? You can write in chat no. So someone asked what factors make the first policy better than time and space. So time and space like inter we are not repeating the same calculations again and again. So we are saving calculation time and space like we can I mentioned this one, right? this storage. So we can store at one place. So initially, if we were using 2 units of space, now we will be using only 1.2 units. So in this way, like we are reducing time also and space also. So I got answers like no. So the actual answer is no, because like they should not necessarily have the same value. This is because like suppose if opponent was also taking advantage of symmetry, then probably the answer would be yes. But now we don't know whether opponent is also opponent is considering symmetry or not. If he is not considering symmetry, then he will be treating those two states, like I mentioned, those two states, like he might be thinking these two states differently. So if he is thinking then differently, then he will be having different values attached to these states. If there are different values attached to these states, then when he reaches these states, then he will be taking different actions in these states. And once he takes different action, now we will have to adapt our policy according to this opponent. So hence, like the answer is no. So necessarily was the key point here. Is there any doubt? They may have different ancestors in game tree. Yeah. From the perspective of opponent. So opponent changes the game here. So now we move to question 6. So question 6 is like this I think sir has also discussed in class. So this is the same tic-tac-toe problem. Consider suppose we are in a state where the winning probability is 0.6. And like suppose we have 3 states and the maximum probability suppose in this state is 0.8, this state is 0.4, this state is 0.2. So while updating the current state's probability based on the next state, so we are updating backwards. Should you back up the suppose like for exploration, we choose a next state which has the, so we are choosing this state. This is purely for the exploration purpose. Should you back up the current state's probability value based on this choice of next state? Given that the agents never stops exploring. This is the key part here. Agent never stops exploring. So there might be a game in which like after a certain level of learning has been achieved, we start exploring and simply start exploiting. But here like it's given that the agent never stops exploring. So it is exploring till infinity. So this kind of epsilon greedy. So some fraction of the time it is always moving that exploratory move. So now the question is, should we be backing up the value or do not back up the value? So is it option A or is it option B? So this is like qualitative question, but if this condition wasn't given, what if given this condition that the agent never stops exploring, like there is a certain answer to this question. So is it like option A or option B? So everyone is saying option A. Yeah, so it's actually correct, like this option A. Well, we should, if we are not stopping exploring till infinity, we are always exploring, then this exploration thing with some fraction of time, this becomes a part of our actual behavior. Maybe with 0.1 probability, we are always 0.1 probability, we are always exploring, and with 0.9 probability, we are exploiting. So this becomes a part of our behavior. So in this way, like it's necessary we back up this value because it is something which has become part of our behavior. So we should be backing up the values so that our model is as close to reality as possible. So this is the answer for this. And is there any query, like any doubt? Okay, so now we will move to 7th question. So suppose we want an RL agent to learn to play the game of golf. So I hope like everyone knows what golf is. So In goals, like there is a hole in field, and the aim is to like get this ball to this hole. And assume that the original reward distribution gives the reward of +10 when the golf ball is hit into the hole. +10. So original distribution is that +10 is given when this ball goes inside the hole, and -1 for any other action or transition. So -1 otherwise. To aid the agent's learning process, we propose. So there is a proposal. This is the original thing. Additional reward of +3 whenever the ball is within 1 meter radius of the hole. Suppose this is the 1 meter radius, and we are proposing that +3 will be the reward given if we reach this circle. So is this additional reward a good idea or not? Why? So again, like this is a qualitative question. So maybe you can write in chat what your thoughts are. Like, will this additional reward of +3 help in learning? Like one option is the additional reward will help speed up learning. Yes, getting the wall within is kind of a sub goal, so it should be rewarded. Third option is no, it will not. It might actually hinder the learning. And fourth is no, it violates the idea that a goal must be outside the agent's direct control. Maybe you can write in chat. Is it option A, B, C, or D? So like people have written C. Mostly I'm seeing C, but there are A and B also. So maybe I'll give you a scenario which will help you understand this situation better. So suppose like the goal of agent in RL is to like maximize the cumulative reward. So if like agent gets in this radius, then it will maybe make a move. It will still remain within this circle and collect reward +3. Again, it will make slight move +3 again. If it makes +10, then like the ball goes inside the hole and game will end at that point. But in this way, like it can be around the circle in the same circle, but not going to the hole. So in this way, like it can keep on collecting these +3 small +3s many times. So eventually, like this reward will be bigger than this +10, which results in end of the game. So what should be the correct answer now? Is it like really helping the learning? Like the goal was to get the ball inside the hole. So now I'm seeing more C. So yeah, like the correct answer is C, because in this scenario we have seen that it is actually hindering the learning, because our learning goal was to make the ball go inside this hole. But what this additional +3 does is the agent might learn to stay in this 1 meter radius circle, but never go inside, because it can keep on collecting these +3 many times. But if it collects +10 one time, then it's game over. So it might learn this kind of thing, that it keeps on being here in this circle many times, and collecting this +3 will eventually lead to a total reward, better total reward than like directly doing +10. So it actually hinders the learning, because it is not like part of the goal. Goal is to get the ball inside this hole. Okay, so I hope like everyone got this. Yeah, so C. So now we move to question number 8. Suppose, okay, so this question is actually similar to one of the questions in the assignments. So pay attention, maybe this might help you there. Suppose that we are given a 10-armed bandit problem, and we are also told that the rewards are deterministic. Keep this in mind. This is important, because rewards are deterministic means like they are not stochastic. So only just one sampling of one arm is enough. So how many times should each arm be tried before we can identify the best arm with 95% probability? So should we like sample, like here we have to give this number for each arm. So should we like sample each arm 1 time, 2 time, 95 times, or none of the above to we identify this best arm with 95% probability? Maybe you can answer and check. So there is an answer A. Again A. So yeah, like it's simple because the key thing here was this deterministic. This deterministic means each arm has a fixed probability, which is not changing with time. Like it is getting deterministic reward. So we are when we are pulling this arm, like we are certain that we will get +1. But if it was stochastic, like if we were getting +1 with maybe probability 0.8 and maybe 0 with probability 0.2, then we will have to sample many times to get this expected reward. But since it's deterministic, then we can like simply sample it 1 time. And this 95 is just given to like deviate you from the answer. This is actually 100%. If you can sample each arm once, and you can be 100% sure that what is the best arm. Whichever give the best reward will be the best arm. There might be a case like where 2 arms have the same reward, but in that case, both arms will be the best arms. So we can be sure with 100% probability. So the answer here is A. So this question will help you in assignment also. Now the ninth question. So ninth question says that suppose that you have been given different drug formulations to treat a particular disease, and your job is to identify one among them. So there are different drugs, and we have to identify the one which that best meets certain criteria with regards to its efficacy in treating the disease. But before you run the experiments, you need to provision for the samples that would be required. So in medical domain, getting these samples is quite hard because drugs need to be tested on living organisms. Like sometimes small animals, rats, monkeys are used. So these samples are hard to obtain. So like the idea here is like you need some kind of estimate that how many samples might be required. So if we treat this as a multi-armed bandit problem, which kind of solution method would you prefer for identifying the best option? So asymptotic correctness, is it the answer? So in asymptotic correctness, what happens is we basically want that when we reach infinity, like a large number of time steps, then we should be picking the best arm. So here it's drug. Regret optimality basically means that the regret should be total regret should be minimal. So basically like we want something like this kind of graph. This regret should be minimal. Is it regret or is it pack optimality? So maybe you can answer in chat. So everyone is saying C, it's pack optimality. Yeah, it's actually pack optimality because pack optimality like kind of gives you a handle on like how many like after how many steps you will start doing optimal. Like this gives like some kind of minimal number of steps that you need to do to reach optimality. So this pack optimality will actually help in this question. So I hope like this is clear. This simple, like the key thing was to get this statement. Now I'll move to the last question of this section. So consider following statements for epsilon greedy approach for a stationary environment. So again, like a similar question is there in assignment, but it's for non-stationary environment. Here they have asked this for a stationary environment. So you need to keep this in mind. So for a stationary environment, always keeping epsilon as a constant, is it a good approach? Like basically you have to which of the following statements are correct. So some of these might be correct. You need to answer which of these are correct. Large values of epsilon will lead to unnecessary exploration in the long run. And cooling down epsilon too fast is problematic as it cannot guarantee correctness in value estimates. So the key thing here to note is stationary environment. So what generally happens in a stationary environment? A stationary environment, the environment is not changing. So once we have explored enough, we can start exploiting. So like in that case, like always keeping epsilon as constant is not a good approach. Because once we have explored enough, maybe 10,000 steps, at that time we will know that this is the best action. So at that point of time, we need to stop exploring, right? So we need to like bring this epsilon down and start exploiting the best one. So this is not correct, right? So second option is like large values of epsilon will lead to unnecessary exploration in the long run. So in this is for epsilon greedy. So suppose if we take epsilon as generally it's 0.1, but if we take 0.5 and with 0.5 we are exploring and 1 minus epsilon again 0.5 we are exploring and exploiting. So in the long run, like we will be exploring like quite enough. So it might lead to unnecessary exploration in the long run. So large values of epsilon will lead to unnecessary exploration, right? And cooling down epsilon too fast, like this thing is important, too fast is problematic as it cannot guarantee correctness. So if we cool down like epsilon, we start with 0.1, but after at second step we decrease it to 0.05 and third step we decrease it to 0.01 and fourth step we decrease it to 0.005 something and then again 0.001. Like we are cooling it quite fast. So maybe in 10 steps this will become quite very negligible. So it will cause problems because we haven't explored enough. We should be exploring enough also, maybe 10,000 steps or something. This actually this number depends on the problem, but you get the idea, right? So this also seems correct, like it is problematic. So the correct answers are 2 and 3. So it's option D, right? I'll check chat once. So yeah, it's option D. So now like I'll show you a demo. So maybe someone can unmute and tell me if he is able to see the Jamboard. Are you able to see the Jamboard? Yeah. So okay. So so this is like a game. So there are 3 coins and these coins are biased. So if it was like unbiased coin, so unbiased coins means that probability of head is 0.5. This. And probability of tail is again 0.5. But these coins are biased, means this does not necessarily hold that probability of head is equal to probability of tail. So we have 3 coins. If we get head, then we get a reward of +1. If we get tail, then we get a reward of 0. So basically the goal in this game is to maximize the number of heads. Because if we maximize the number of heads, then our reward will automatically get maximized. So like there is a demonstration in which like I show you this game. So I hope like you guys are familiar with this collab. So in collab, you can like directly start running your Python codes. So Python is actually, so we have 3 coins. We don't know the probability of head of any of these. So this will demonstrate you the issue which we face in like this exploitation exploration thing. So we don't know what is the probability of head in each of these coin. and the aim is to get maximum heads. And now the number of tosses which we are going to do is 20. So in this 20 tosses, we need to get the maximum number of heads, and we don't have any information about the coin. We can get the information by tossing. So maybe like we will try with coin 1 first. So let's see what happens with coin 1. So coin 1 gave us head. So probably maybe it's a good coin. Let's try it again. So now it gave tail. So it gave head at 1 and tail at 1. So now maybe like we can explore the coin 2. Let's see what it gives. So coin 2 gave tail on the first toss. So probably it's a bad coin. So maybe like at this point we can try coin 3. Let's see what it gives. So coin 3 gave head. Let's see, like we try coin 3 one more time. It again gives head. So at this point, like you might have an intuition that maybe coin 3 is the better one. So let's see this coin 3. Again, it gives head. Now we try it again. Again, it gives head. So we keep on exploiting. Now we are like kind of in the scenario of exploiting. We have kind of realized that coin 3 maybe is the better coin of these. So again head. So 5 consecutive heads. Let's see. Again head. So it gave us 6 head. Coin 3. 7 heads. Now it gave a tail. Now you might have some doubts about coin 3. Maybe it gave a tail, although it gave like how many heads? 1, 2, 3, 4, 5, 6, 7. 7 heads and 1 tail. Maybe like we haven't explored coin 2 that much. Let's try coin 2 once more. So we are now exploring. It gave us head. Maybe try coin 2 one more time. Let's see. It gave us tail. So we can kind of figure out that coin 2 is slightly bad coin. Maybe like we will try coin 1 once again. It gave head. Let's try one more time. It gave tail. So it's kind of 50-50. So till now, like at this point, like we can be sure that coin 3 is the best coin. So now we begin the phase where we are only exploiting. So we will enter only 3. We got head. Again, we got head. So we got tail. Regardless, we feel that coin 3 is the best one, so we will keep on exploring it, exploiting it. It gave 2 tails. Still, like the probability of head is much higher compared to other 2. We'll exploit it. So what is the like final thing? So we got total heads of 13 out of 20. Now let's see like what were the actual probabilities of these coins. So the probabilities of head of first coin was 0.4. The probability of coin 2 was 0.6 and coin 3 was 0.8. So coin 3 was indeed the best coin. But in expectation, we should have gotten 16 out of 20, like because it's 0.8. So, but we got like 13 heads. So this is like the regret. 3 is the regret. We could have gotten 16 if we were like kind of exploiting coin 3 from the beginning in expectation. But we got 13 because we wasted some of our attempts on coin 1 and coin 2. So I hope like you understood this exercise, right? Maybe I'll go to chat once. So you guys like understood this exercise, right? So maybe like let's try this one more time. Like this time I'll change the probabilities. So let's bring them close. 0.3, 0.3, and maybe coin 3 we keep it better again, 0.4. So let's run it again. So again, like it's kind of cheating because we know which is the better coin, but act as if you don't know which is the better coin. So maybe like we will try with coin 1. Now we got head. So we might be confident about coin 1. We try it again. We got tail. So now we are in a dilemma, like maybe like we should try some other coin. Let's see coin 2. It gave tail on first. Let's go to 3. It gave head. Try it again. Give tail. Now like since it's close, like you know the probability, it's close. So what should we do? We go back to coin 1 again maybe. Let's see. Coin 1 gave tail again. So maybe coin 2, we don't know. Maybe it got unlucky and got tail at the first attempt. Let's try coin 2 one more time. Coin 2 got again tail. We might think like it's a bad coin. So again, like we will move to coin 3. So it also gave tail. So now we are in a dilemma again. Let's try coin 2 one more time. Maybe it gives head and all of 3 becomes equal in our perspective. And it gave head. So now we have like it's like all of them are equal in expectation. So maybe let's try coin 2 one more time. Let's see. Give head again. 50-50. Coin 2 looks better at this point. But even though we know that coin 3 is the best one, but this is the expectation which we are seeing. It gave tail. Now maybe we can try coin 3. Let's see what it gives. It gave tail. Now we are like slightly worried about coin 3. Now let's move to probably coin 1 one more time. Let's see what it gives. It gave tail again. So we might start thinking that coin 1 and coin 3 are not that good. So maybe like we start with coin 2. Coin 2 is like it's giving 50% heads, 50% tails at this time. Let's try coin 2 again. It gave tail now. Now tails are more. So maybe like we explore coin 1 again. So it gave tail. It's definitely a bad coin. Let's see coin 3. So it gave head. Maybe like we try coin 3 once more. Give tail. So it's like more tails, less heads. We try coin 2 again. So just one toss left. And coin 2 gave us tail. Maybe try coin 3. So what is the like final thing? So we got like 7 heads. And in this like, although we knew in back of mind that coin 3 was the best coin, but it gave like 3 heads and 4 tails. And this coin like it gave 3 heads and 5 tails, and this gave 1 head and like 4 tails. So like even though like probabilities were 0.3, 0.3 and 0.4, coin 3 was the better coin, but we couldn't like in these 20 tosses, we couldn't get the feeling that coin 3 is better. So maybe like this problem might have required more exploration. Maybe we might have tried with 100 tosses. So maybe like I will be sharing these codes with you. You can try with 100 coins. So again, like if the probability was 0.4, we should be getting almost on expectation 8 heads, but we got 7. So this again, one is the regret here. So this was the like demonstration which I wanted to show. I hope like you understood this demonstration. Yeah, so now I'll start sharing the slides again. So I hope like the slides are visible now. We have seen a like decent demo of how this exploitation exploration dilemma, like it's not easy. Like you, if the arms are closed, like in the case like point 0.3, point 0.3 and point 0.4, we couldn't differentiate much and we required more exploration. But like when the probabilities were like 0.2, 0.6 and 0.8, like 0.4, 0.6, and 0.8. Then we were able to like kind of get the idea that 0.3 is the better coin. So like this exploration dilemma is quite important in reinforcement learning. So keep this in mind. So now we move to assignment 1. So in assignment 1, like I'm not supposed to give the answers, but I'll try to give you the concepts because like the deadline is still not over. But maybe like you guys can tell me the answer. I'll guide you through. So this is the like first question. So which of the following is not a useful way to approach a standard multi-armed bandit problem with end arms? And the assumption is that bandits are stationary. So how can I ensure that the best action is the one which is mostly selected as time tends to infinity? What is this? Like this is called asymptotic correctness, right? How can I ensure that the total regret as time tends to infinity is minimal? This is called regret optimality. How can I ensure an arm which has an expected reward within a certain threshold of the optimal arm, like this y epsilon, is chosen with a probability above a certain threshold, maybe 1 minus delta. So, like this is the formulation of back optimality. What is the fourth option? How can I ensure that when given any two arms, I can select the arm with a higher expected return with probability above a certain threshold? So the key point here is any two arms. Now suppose if the arms are like this, suppose I'll give you 5 arms, A0, A1, A2, A3, and A4. This is maybe expected reward is 0.8, 0.6, 0.4. This is maybe 0.2, 1.5. This is maybe 0.17. So, like here, like the idea is like that any two arms. Do we really care about these two arms? Like, suppose if we are taking A3 and A4 arms, do we really care that we should be selecting A4 with some probability threshold more than A3? Like maybe you can answer in chat. Should we care about this? So yeah, like basically like this is enough to reach you to like help you reach the answer. Now I'll move to question 2. So someone was like saying in chat that I should go to non-stationary system of probability assignment. So like basically like we are moving in a step-by-step manner. So the thing is like it's not just that. Okay, can we go to for non-stationary system of probability assignment in demo? Yeah, like non-stationary. So basically in non-stationary, like you'll have to like kind of keep on changing the probability of the arms at each time step. Not at each time step, maybe after a few time steps, you will need to change the probability of the arms itself. So in that case, like we will never be getting to the best arm, because once we decide that some arm is the best arm, maybe the environment changes and its like probability of head will decrease, and some other arm which was poor initially might become the best arm. So we need to keep exploring, like continue exploring. So in non-stationary environment, you might have seen that we keep the epsilon as a constant. So this was the reason. So in non-stationary, you can like you need to keep on exploring. So maybe like I will be sharing you the code. You can modify it, like and just put a loop in which like this probability I have assumed it to be constant. You can change after some time step. Right? Okay, so second question is, so yeah, like there was one more thing in chat that Can I move to the okay, this is addressed. So what is the decay rate of the weightage given to past rewards in the computation of Q function in stationary and non-stationary updates in the multi-armed bandit problem? So there are like stationary and non-stationary scenario. So first option will correspond to stationary and second will correspond to non-stationary. So you have to like give the answer that how this decay rate like falls off. It can fall like exponentially, it can fall like linearly or hyperbolic. So these are the like options here. So maybe like I'll give you a hint how to do this for non-stationary updates. So you can see like here, like this is the formula, right, of Q value update for non-stationary. So non-stationary like alpha is constant. So this is the Q at t plus 1 for action A is 1 minus alpha times previous estimate of Q value plus alpha times the reward. So let's put the value. So let's take this t equal to 0. So at t equal to 0, like Q1 of A will be equal to 1 minus alpha times Q naught of A plus alpha times reward collected at 0 times that. Now, similar way we can write put t equal to 1. So this is like t equal to 0, t equal to 1. So Q2 of A will be equal to 1 minus alpha times Q1 of A plus alpha times R1. So now, but from this equation 1, you know the value of Q1 of A. So you can put this value here and see how it opens up. So it opens up like this 1 minus alpha square Q naught of A plus alpha into 1 minus alpha times R naught of A plus alpha times R1. Now this is suppose our equation 2. Now we write the equation again at for t equal to 2. So it will become this t plus 1 will be 3. Q3 of A will be 1 minus alpha times. Now this Q2 of A, like you can put it from here in the next step, plus alpha times the reward captured at second step. So when you open this up, put this here, it will become 1 minus alpha times Q naught of A plus alpha 1 minus alpha square R naught plus alpha. So basically, like you can see, like these are older rewards. R naught is like when we are at the this time step t equal to 2, R naught will be the oldest reward. This will be R1 will be like slightly older, and R2 will be our newer reward. So maybe like consider alpha to be 0.1. So this weightage. So this is the like initial Q value estimate. Remember like initialization. So sir mentioned at one point that initialization doesn't matter much because like you can take it minus 100 plus 100 0 because this you can see when we do for a long number of steps, this will be like 0.9 maybe power 100. So this will be very small quantity. So this will like kind of remove the impact of this. This will like this whole quantity might tend to 0. Now the question which is asked is like how these weights fall off. These weights of these rewards fall off, older rewards. So newer reward is 0.1 as of now. 0.1 is getting multiplied by zero point 0.9 for this alpha. 0.1 is getting multiplied by zero point 0.9 square. And when we do it more and more, like if suppose we are at time step 10, then it will be 0.1, 0.9 raised to power 1 square, then it will be zero point 0.1 into a zero point 0.9 something cube, then 4. So in this way. So can we write this entity as this one, 0.1 into, so this is simply rearranging. This can be written as 9 by 10, and you can write like 1 upon 10 by 9, and then like you can put this negative sign. So this format is similar, right? A, like there is a constant scalar, which is 0.1. There is another constant which is greater than 1, A, B minus X. So this quantity is something similar, right? You might have seen this quantity in form of E raised to power minus X into some constant. So I hope like you get the idea like how this is falling. So this is for non-stationary updates. So in stationary updates, again, like you know, like this alpha decays, like it's like 1 upon NA plus 1. So again, like you can open it up in a similar manner and see how it's falling. So you can get the answer from that. I hope it's clear. I'll check the chat if there is some query. Okay, so no query. So maybe like I'll move to next question. So this question is like so this is the update rule which we considered in last question. So it's just they have rewritten it. So this I wrote it like 1 minus alpha ut of a plus alpha times rt. You can multiply this, open it up, and it becomes same format. So select the value of alpha that we would prefer to estimate Q values in non-stationary. So this is the key term here, non-stationary. In non-stationary, the goal is to like keep on exploring. Like we never stop exploring because the point, maybe there comes a point where we might think that this is the best arm, and that point the environment changes and that arm is no longer the best arm. So maybe some worse arm became the best arm. So we need to keep on exploring. And how to ensure that exploration keeps on going till infinity? Maybe like we might have to keep alpha as constant. So I hope like you'll get the answer from this. Is there like any doubt? Oh, there is no more doubt. So I'll move to question number 4. So question number 4 says that this is assertion reason kind of question. So basically we need to verify that whether these statements are true and like one explains the others or not. So taking exploratory action is important for RLAs. This is kind of true, right? You know this because exploration is important to reach the best action. And if the rewards obtained for actions are stochastic, an agent which gave a high reward once might give lower reward next time. So suppose there is an arm which gives +1 with probability 0.8 and 0 with probability 0.2. So this is an stochastic scenario. If the rewards are stochastic for actions are stochastic, an action which give high reward once. So it might happen like we will generate a random number from like, you know how we sample from our distribution through its CDF. So we will generate a random number between 0 and 1 and see if it's suppose if it less than 0.8, then we will get reward +1. If it's in between 0.8 to 1, then we will get 0. So it might happen, right? So this is also like true. We might get a high reward once and lower reward at the next time step because it's according to probability. So both of them seems to be true, but is it like this? Does the reason explains the assertion? That is the question we are looking at. So maybe like these two we can rule out because they're mentioning that this statement, second one is false. But the question is like, is it the correct explanation? Do we need to explore because of this reason that we need to? So maybe like I'll give you some idea. So this reason, maybe if the assertion was like this, that we need to sample many times, sample an arm many times, and this might be the reason, right? That it can give high reward once, lower reward next time. So the assertion might be we need to sample each arm many times in stochastic environment. And taking exploratory actions is important for RL agents. It is important because it helps in getting to the best arm. Maybe like if we start exploiting quite early, we might miss out on the best arm and keep on exploiting the not the best arm, second best maybe, or even a worse arm many times. So exploration is important. So I think like you get the idea like what might be the answer. So if there is no query in the chat, so someone asked why constant? Because like the environment was stationary in that question. environment was non-stationary. So if it's not constant, suppose if we decrease the value of epsilon close to zero, so it becomes zero at some point, then we basically stop exploring and we are simply exploiting. Maybe if the environment changes, because since the environment is non-stationary, now the environment changes and the best arm which we identified till this point becomes a bad arm, and maybe the second best or third best arm becomes the better arm. So we need to keep on exploring. We cannot decrease this. So this epsilon should be constant in non-stationary environments. Now the fifth question is we are trying different algorithms to find the optimal arm for a multi-armed vending. We plot expected payoff versus for each algorithm we satisfy. So our time is starting from, maybe I'll draw this. Our time is starting from 0. So optimal expected payoff is 1. And basically we need to give the function which will have the least regret. So maybe you need to plot the graph of these functions and see which one gives the least regret. Maybe some might be like this. So this will give lesser regret compared to this one. This area will be more for that. So basically the idea is to plot these functions. So this option, maybe you can rule out. This is highly unlikely at same regret because these seem different functions, right? So basic thing is to plot these graphs and see which one has the least regret. So how do we plot graph? So one thing is to get some maybe x value and calculate the value of t, and in this way for another x value you plot this. You can do it manually many times, but since we are in a reinforcement learning class, I have written code for it. So I am using matplotlib to plot this. So maybe I'll take 30 points, and y optimal is obviously 1 for all these 30 points, and option A is 10h for these 30 points, and YB, option B was 1 minus 2 raised to power minus I for these 30 points. And the third option was this x upon 20 for x less than 20 and 1 after that. So I have written two lists. So it's upon 20 in range for the first 20 points up to 20 from 0 to 20. So basically in Python this second bracket means that you are not including that number. So it's before 20 and 20 is included here. So after that it becomes 1. And this operation we are concatenating these two lists into one so that it becomes a 30 element list. Now I'll be plotting this. So you can use matplotlib to plot this. And let's see the graph basically. So optimal is this one, black one. Red one is option A. Option B is blue one, and option C is green one. Basically, the thing is you need to answer which of these three graphs have the least regret. Obviously, we have ruled out option D correctly because clearly the areas are not same. So but one more thing to note is that in exam, how will, if some question like this comes, how will you do it in exams? Because in exams, you won't be having access to matplotlib and to plot, and manually plotting will take a lot of time, right? Maybe I'll look in chat once, see if there is some question. Show the code again. Okay, so please explain in brief the option A and B of question 4. Okay, so question 3 constant was clear. Question 4, A and B option. So question 4. Okay, so basically I'm not supposed to give the answer, but you get the idea. These two are true statements, but does one offer the explanation of other? So you need to think in that way. Because I mentioned that this reason would have been more appropriate if the assertion was something else, right? So maybe like we will discuss it later, like when the deadline gets over. But as of now, I can give you this only. So another question in chat was, show the code again. So I'll show this code again. Let's see, like, so yeah, like, so in what part like you are having doubt? Maybe you can write in chat. I'll wait a few minutes. Or maybe unmute yourself and plotting part. Okay. So plotting part. Okay. So this is like basically like I'll explain the. So basically like there is a notebook. I'll be sharing this notebook with you, and like we are importing a math library and matplotlib. So this part I think you got it. Like we are actually getting the list of these numbers, like these functions basically. And once we have those lists, like so basically like this PLT function, like matplotlib has a plot function in which like we pass the x axis values and y axis values of like these graphs. So I'm coloring it in black, then red, then blue and green. And X level, this basically gives the level to time, and Y level expected payoff. And legend means basically like it gives this. So it actually maps the color coding to the options. So I hope like this is clear. Got it. Okay. So I hope like you'll get the answer from this one. So now let's move to the sixth question. Sixth question. So yeah, so this one, like I have mentioned before also, like I think we saw a similar question, but that was for a stationary environment. So this is for non-stationary environment. So in non-stationary environment, like I have mentioned this many times that it's good that you keep it constant. So keeping a small constant epsilon is good approach if the environment is non-stationary. So this you already know, right? So larger values of epsilon will lead to unnecessary exploration in the long run. So in non-stationary environment, we are either way like keeping it constant. So once we are keeping it constant, do we really need to have large values, or we can simply have small epsilon values? So will large values of epsilon lead to unnecessary exploration? This is the question which you need to answer. So I think like you'll be able to answer this. And for a stationary, so this point corresponds to stationary environment. Decaying epsilon value close to zero is a good approach as we reach, as after reaching optimality, we would like to reduce. So this is for stationary environment. Decaying epsilon value to zero is a good approach as after reaching, we would like to reduce exploration. So this also like, I think for a stationary environment, you will be able to figure it out that which of these statements are correct. I'm not sure like this actually meant for a stationary environment because at the top they mentioned it non-stationary. This is slightly ambiguous because how did they put a statement for a stationary environment? But like you get the idea, like you can get what is true and what is not true. I hope like there is no more question. Okay, then like I'll move to question number 7. So question number 7 says, following are the two ways of defining the probability of selecting an action arm. Yeah, like so this is what we call it softmax. We have seen one question of this also, calculation one. And this one is not softmax, but like just exponents of this e. So what might be the problem with this one? I think like in lecture also it was discussed that this QTA might be negative, right? So it might result that maybe it's -1 upon 20 kind of thing, which might not be a probability kind of thing, because probability is supposed to be in 0 to 1, right? So I hope like this will help you in reaching the answer. So I think like this is sufficient. Like, are both of these like good formulas? Like, maybe not, because first is definitely not. One is better because it is differentiable, but second can be different. Second is also differentiable, right? Like you can use the chain rule and you can still differentiate it, and requires, although like less complex computation, yeah, but but this differentiable part. So maybe like I think that will help you the answer to get to the answer. Requires less complex computation, but keep in mind this and, right? And means both have to be true. And first is not true, right? Because second is also differentiable. What is the issue? Like you can apply chain rule, just one more function. Maybe now I'll move to question number 8. Which of the following best refers to pack optimality solution to bandit problems? So here again, epsilon is the difference between the reward of the chosen arm and the true optimal reward. Delta is the probability that chosen arm is not optimal. So in this case, 1 minus delta will be the probability that the arm is optimal, and n is the number of steps to reach pack optimality. So in this question, basically, you have to answer which of these best refers to the pack optimality solution. Like, what is the crux? Like, are we like given delta and epsilon? So what is the main goal in like pack optimality? Like, we basically kind of try to get to the optimal solution in minimum number of steps, right? So we kind of want to minimize that. So I think like that should be able to reveal you the answer. Yeah, I think that should. So now let's move to the ninth question. So yeah, like a similar question in which we saw in problem solving. So suppose we have a 10 armed, again here also like it's 10 armed, which rewards for, so again it's deterministic and in the range 0 to 10. Which among the following methods will allow us accumulate the maximum reward? So the key term here is deterministic. If the arms are deterministic, then as we saw in the previous question, we need to sample each arm only once. So like, do we need to be epsilon greedy with epsilon 0.1? Not really required, because maybe in like 10 samples we can figure out like which is the best term and start exploiting that term. So it's not really necessary. So I think you can rule out these two. So greedy, definitely we need to be greedy, but with initial reward estimates. So this means like how many times you need to sample arms in total. So one for each 10 arms, I think you should get the answer. So now this is the last question of the assignment, which says, which of the following are correct and valid reasons for sampling from a softmax distribution instead of using an epsilon greedy approach? So basically, like this is talking about what are the advantages of softmax. So softmax exploration makes the probability of picking an action proportional to the action values. Yeah, this is definitely right. By doing so, it avoids wasting time in obviously bad actions. Because yeah, like if some action is very bad, then it will assign like very low probability, maybe 0.01, something like that. So it will kind of avoid those. So this looks okay. Now Second option is we do need to worry about decaying exploration slowly. We do not need to worry about like the epsilon greedy case. Softmax exploration gives us asymptotic correctness even for a sharp decrease in temperature. Okay, so sharp decrease. So what happens like, so you remember that equation in which softmax was like Q value of some action, and there was this parameter beta. This is called the temperature parameter. And again, like the sum will be upon all action maybe alpha belong to action set and e raised to power q of alpha on beta. So what happens when this temperature parameter is quite low? So this will be maybe we can consider it's 0.0001. So basically like you can think like this is like 10 raised to power minus 4. Then it basically goes into denominator. Like it is in denominator. Now it goes to numerator. So it will basically multiplying by 10 raised to power 4. And this is like amplifying the effect, right? So it will softmax will kind of become kind of max. So it will like maybe assign very high probability to the arm which is the best 0.9999 something. And so this should help you like, so basically like it's like max arm we are getting 0.999, for all other arms it's very less. So maybe 0.001213 something like this. So is it like, is it, does it give asymptotic correctness even for sharp decrease in temperature? Like I don't know, like you need to think about this and see. Now the third option is it helps us differentiate between actions with action value estimates Q value that are very close to the action with maximum Q value. Yeah, so this is kind of correct there because using epsilon greedy, what happens is it will give like 1 minus epsilon, which will be a large number, maybe 0.9 to the best action. And this remaining 0.1 gets divided into all the other action. But the softmax might give like maybe 0.4 to best action, but second best will get maybe 0.3, third best might get zero point 0.2, something like this. And others might share like this remaining 0.1. This might be. So this also looks correct, but 1 and 3 are definitely correct. Now you need to like think about this second one. We don't need to worry like, so once you get the second one, you will get the answer, right? Is it like true or false? Yeah, I think like this is the like last question for assignments. So now like there are some reading material. So this is like Sutton and Barto chapter 1, like it's like basic reinforcement learning. So like maybe the first two lectures correspond to this chapter. Then Sutton and Barto like this is the standard textbook which we will be following, and this is called Bible of RL. So it's a good habit to like read this. And Sedan and Barto chapter 2 up to section 2.5. So after 2.5, like 2.6 and further, like those topics will be covered in week 2. So if you want to be ahead, then you can read them. But try to read till section 2.5. It's a good habit. And this is the optional reading. So Russell and Norwich, they have a book called Artificial Intelligence. In that, like there is a chapter 2. So it's like about agents and environments. So this is like this concept is quite like integral to reinforcement learning. So you might want to get some intuition about that from this chapter, but it's optional kind of. But try to read this book with lectures. Like this will improve you a lot. So now like I think like that brings us to the end of the lecture. But before leaving, like if there are some more doubts, I'll try to solve them. Like you might mention it in the chat if there are some more doubts. Or maybe like we don't have many participants now. So maybe you can like kind of unmute yourself and ask if there is any doubt. Otherwise, like we will meet in like next Tuesday. So this is like every Tuesday. Okay. So excellent session. Yeah, thank you. Yeah, I hope you learned a lot. So I'll be continue in this pattern only.
Thank
Yeah,
you.
so, yeah, right. You're welcome. Okay, so maybe like if you have some general doubts about RL, you can ask. Maybe like I think we have some time. There are none, then we'll meet in the on next Tuesday, same time, same link. I'll be sharing this slides, recording, and also like the two notebooks. One of that graph for regret, and second that bandit exploration exploitation dilemma. So you can experiment with those also. Maybe like they might reach you later, not now. I will be sharing with NPTEL today, but generally like sometimes there are delays. So certain derivation professor is skipping in lecture. Can you derive them here? So basically like he's not like skipping. So week one was like introduction. So in this, like the aim was to get you familiar with the terms and like basic concepts like exploitation, exploration, dilemma. Now these like the suppose the I'll show you like these were the topics of like lecture one. So introduction to RL, this was pretty basic. RL framework and application. This will keep on getting used over and over again. Immediate RL, just one of the concept. Bandit optimality. So the next week, like there will be a I think whole week is devoted to this bandits. So all those derivations and all like will be done there. And this value function based method, this will again come up like when we actually move to learning. Like bandits is like one special case of reinforcement learning in which like we do not care about the state, we care only about the action and reward. So the state is like kind of same every time. So in that, like when we move to proper RL, like this value function based methods will come in great detail. It will include q learning, SASA, expected SASA, and all those algorithms. So that will come later. His assumption about us is bit high, that's why maybe. Yeah, so might be because like this course is generally like this requires some expectation. Like this is a like course which is meant to be taken by like even the master's students, also the PhD students, and some professionals also from academia. You see like some of the faculty members were there, even like maybe some people who didn't attend, they might be from industry also. So this course in like is to like cater to the requirements of all of them, not just like bachelor's students or like those who are like not that comfortable. So this is slightly like, yeah, that level is high, but yeah, like you need to like study well and keep on improving on the concepts. It will help you later eventually. Yeah, so I think like that's it from my side. I'll stop sharing. If there are any more doubts, you can. Okay, thanks. Yeah, welcome.
Sir, one more question, sir, please.
Right. Yeah.
Uh, actually, from the exam perspective, is it mandatory to go through the books, sir? Otherwise, I am following the video lectures of professor and your live sessions kind of things. Please kindly guide me in this aspect, sir, because I'm here totally 100%. I'm unable to go through with the books, sir, study materials. Really.
Yeah.
Please kindly share your opinion.
So like basically like definitely like reading the book will help you, but if you keep the concepts right, then you can solve the questions like even without reading the book also. Like so the basic aim is to get the concepts right. Once you have the concepts right, then you can solve the questions. Because like I'll give you my example. Like I took a reinforcement learning course, like not this one, but a separate one. I didn't get time to read the book, but I focused on getting the concepts right, and it helped me solve the questions in the exams. So the focus should be on getting the concepts right, but I'm not saying that reading book is waste of time. Like it will definitely help you. If you get the time, then definitely try to read the book. It will be a new experience, and it has a lot of questions also, so it will help you get more familiarity. And maybe like, I don't know, I haven't taken this exam. Maybe some of the questions might be adapted from the book itself. So it might help if you actually read the book. But the focus should be on getting the concepts right. Once concepts are right, then you can solve questions even without reading the book. So it's kind of trade-off. Yeah, I hope you got it. Yeah. So I think, yeah. So if there is any more doubt, you can ask me. Otherwise, like I am kind of closing the session. Okay. Yeah, thanks. So yeah, good night, everyone. So let's meet on next Tuesday. So I'm stopping the recording now.